Cloud formation is a fascinating meteorological phenomenon intricately tied to the Earth's water cycle. Understanding the processes behind cloud formation involves delving into atmospheric dynamics, including the role of temperature, humidity, air pressure, and various lifting mechanisms. In this exploration, we will unravel the complex journey from water vapor to the formation of the diverse clouds that populate our skies. The water cycle, a prelude to cloud formation. The water cycle is a continuous and dynamic process that drives the movement of water between the Earth's surface and the atmosphere. It begins with the evaporation of water from oceans, lakes, rivers, and other bodies of water. Solar energy heats the Earth's surface, providing the necessary energy for water molecules to transition from liquid to vapor phase. As water vapor rises into the atmosphere, it undergoes cooling, a critical factor in cloud formation. The cooling can occur through various processes, with adiabatic cooling being one of the primary mechanisms. Adiabatic cooling happens as air rises and expands in the atmosphere, experiencing a decrease in pressure. As the air expands, it cools, and if it cools sufficiently, it reaches its dew point, the temperature at which air becomes saturated with moisture, leading to the formation of visible water droplets. Condensation nuclei and the birth of cloud droplets. For water vapor to transform into visible cloud droplets, it requires a surface to condense onto. This is where cloud condensation nuclei come into play. CCN are tiny particles suspended in the atmosphere, including dust, salt, and other aerosols. These particles serve as nucleation sites for water vapor to condense and form droplets. As air cools and reaches its dew point, water vapor condenses onto CCN, initiating the formation of microscopic water droplets. The aggregation of these droplets marks the inception of a cloud. The presence and concentration of CCN in the atmosphere influence the size and characteristics of the resulting cloud. The diversity of clouds. Clouds exhibit a diverse range of forms, each influenced by factors such as altitude, temperature, and humidity. Three primary cloud types based on altitude are high-level clouds, mid-level clouds, and low-level clouds. High-level clouds, above 20,000 feet. Cirrus clouds, characterized by wispy and feathery appearances, are common high-level clouds. Composed mostly of ice crystals due to the lower temperatures at these altitudes, cirrus clouds often signal fair weather but can also precede a change in atmospheric conditions. Mid-level clouds, 6,500 to 20,000 feet. Altocumulus and altostratus are examples of mid-level clouds. They consist of both water droplets and ice crystals, contributing to their varied appearances. These clouds often create a layer of cloud cover leading to diffused sunlight. Low-level clouds, below 6,500 feet. Stratus clouds form in stable atmospheric conditions and cover the sky like a blanket. Stratocumulus clouds are characterized by a mix of cloud layers and clear patches. These clouds often bring overcast skies and may be associated with light precipitation. Mechanisms of cloud formation. Apart from adiabatic cooling, two significant lifting mechanisms contribute to cloud formation: frontal lifting and orographic lifting. Frontal lifting. Fronts occur when two air masses with different temperatures and moisture levels meet. The warmer, less dense air rises over the colder, denser air, leading to frontal lifting. As the air ascends, it cools, and if it reaches its dew point, clouds form. Frontal lifting is often associated with the development of precipitation and the creation of various cloud types. Orographic lifting. Mountains and elevated terrain can force air to ascend, triggering orographic lifting. As air rises, it cools and clouds form. The windward side of the mountain typically experiences increased cloudiness and precipitation, while the leeward side, or rain shadow, may be drier. Stratospheric clouds and ozone depletion. Cloud formation is not confined to the troposphere, the lowest layer of the Earth's atmosphere. Polar stratospheric clouds, PSCs, form in the stratosphere, particularly in polar regions. PSCs play a crucial role in the depletion of ozone. Chemical reactions on the surface of PSCs contribute to the release of compounds that in turn lead to the breakdown of ozone molecules, contributing to the formation of ozone holes. Conclusion: a symphony of atmospheric processes. In conclusion, cloud formation is a symphony of atmospheric processes orchestrated by the interplay of temperature, humidity, air pressure, and lifting mechanisms. From the initial evaporation of water to the condensation of water vapor onto cloud condensation nuclei, the journey is intricate and multifaceted. Clouds, with their diverse forms and characteristics, serve as visual indicators of atmospheric conditions and play a crucial role in Earth's weather patterns.